Why are we counting? Ooh, are we doing a video?
Greetings and welcome, friends of all ages, mathematicians of all planets, because that's right, math is a universal language, although these words are in English. Today we're talking about, well, we're actually starting a brand new zone. What? We're exploring quadratic. You might remember that word. That's describing polynomials that have a second degree. Quadratic functions. So I'm talking about inputs, outputs, X, Y, T-chart, blah, 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 graphs, stuff like that. And inequalities, which that'll show up a little bit later on in the chapter. But today we're specifically honing in on solving quadratics by graphing. And I've got a handful of vocabulario things here coming at you. And first of all, quadratic function is a function that has a degree 2 for its variable. Parabola is the graph of a quadratic function. Now, crazy thing, X intercepts, solutions, roots, and zeros are all really synonymous with each other in a sense. I mean, X intercepts is kind of talking about the graphical situation. These ones refer to more the algebraic, so to speak, but these are actually always the same as the X intercept anyway. So they're more or less synonymous. So the X intercept is the intersection where a graph crosses the x-axis. Solutions, roots, or zeros are the values of the variable that make a quadratic equation true, and the same as the x-coordinate of the x-intercept, right? So they're the same. Y-intercept is where it crosses the y-axis. Vertex. Let's see. Let's get a little picture going here. Maybe that'd be nice. Little nice picture here for you. Boop, ba-doop, 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 boop, boop. Actually, let me scale this. Get a nice little thing going here. 10, 10. That sounds good. But bam. So, for us to get started here, I'm going to draw a picture and just label some of the vocabulary here for you so you understand what's I'm talking about. So, right, here's a possible graph. So you'd have something called the vertex. So let's say the vertex was like here.
That's not an even graph.
No, I didn't. Yeah, I didn't include the bottom. So here's what's called the vertex. Perhaps you've heard of those before. The parabola. We'll talk about a little bit more about some of these points here coming up later. But the parabola would look something like this. These are actually points on a specific parabola that I'm making up right now. And the parabola is this interesting curve. Let's see, 6. It actually would cross way up here somewhere, but that's fine. And it's a curve that gets steeper and steeper, faster and faster. It would be wrong to describe it as a U shape because a U actually gets like perpendicular at some point. Parabolas never do. It would be wrong to describe it as a V shape because a parabola has a smooth curve, a V is pointy, and also a V shape has linear behavior on the ends. This graph actually gets steeper and steeper, faster and faster. It's related to an x squared function. So I mean, even think about that. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So each of these heights are getting higher and higher, faster and faster. So this does go infinitely high, so to speak.
Why are you putting some on lines and some inside boxes?
Because the tick marks are still halfway between those numbers is all. So here's like 4, here's 3, here's 2, here's 1, here's 0. I don't know. So my scale was not all labeled or not all on the grid. So so here we go. So this is a parabola. It's this interesting curve. There's all sorts of crazy properties about parabolas, flashlights, and things like that. Parabolic skis you might have heard of. Satellite dishes are parabolic. Paths of projectiles are parabolic when you exclude wind or friction. And you're only accounting for gravity and an initial velocity at a direction, blah, blah, blah. So parabolas, all sorts of wonderful uses. Angry Birds love them. Good stuff. So let's take a look at some of these words now. So the X intercepts would be this point and this point, just where the parabola crosses the x-axis. We'll refer to this, let's say this one is S1, comma 0 and S2, comma 0. All right, would be the ordered pairs representing those intercepts. The S1, S2, you don't necessarily have to worry about too much right now, but that language shows up a little bit later in some formulas. The Y-intercept is actually going to be all the way up here somewhere. Let's see, what's 7 more than 5? Yeah, it would have been 12 is where this Y-intercept would have crossed. So I'll just label this as the Y-intercept. And that would have been 0, comma, we'll actually refer to that as C. You'll see Y later on. And let's see, what else do we got? So it says the vertex is the maximum or minimum of the parabola. So notice this parabola, I described this as opening upward, and the vertex was the bottom of it. So it's the minimum point in this case of the parabola. It's also, you could think about it as the turning point where the slope changes direction, right? Like I'm going downhill, 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 slowing down, and then, now I'm going uphill, right? So
It's where it does a little flip roosty.
yeah, it changed direction there. So that's the vertex. The slopes change direction. These are actually negative slopes, negative slopes. That's an interesting slope. And then a positive slope, positive slope. What slope would this be?
Equal.
0.
It's a 0 slope. So that's actually right there a calculus concept where the critical points of a curve can be found by examining the instantaneous slopes when they are equal to 0. So oddly enough. So it's like if I was on a roller coaster. At some instant moment I was horizontal to the ground, my slope was 0, sort of thing. And then the other thing is axis of symmetry. I think you've heard of that before. Axis of symmetry is the line, so to speak, that the parabola is, I guess I'll say, symmetric over. It's a mirror image over this line, like this. So here's my axis of symmetry, so AOS. And the axis of symmetry is an equation. In this case, it will always be x equals h, where h, of course, is the x-coordinate of the vertex, h comma k. So that's just some of the labels, so to speak, and what we've got going on for our parabola lingo. Good stuff. So let's talk about quadratic functions more specifically. So, quadratic functions are like the following. You can kind of write them, well, I guess you could technically use different variables for some of these, but we essentially will have a couple possible names or types for them. And you've seen this before as well. So y equals ax squared plus bx plus c is, I guess I'd call that, standard form for a parabola is something different. General form, yeah, that's pretty much general. Man, even that's not quite right. It's not vertex form. Well, the arrangement of this is called standard, but anyways, don't worry about it. But this is often how we'll have it set up, right, highest exponent to lowest sort of idea, 2, 1, 0. It's quadratic specifically because the highest degree is 2, and A, B, and C, those are the same A, B's, and C's that maybe you've done some work with a quadratic formula before, like so. Now, I also might write it in this format. Has anyone ever seen this before?
Yeah.
Excellent. This is read as f of x. All right? It's the same as y. F of x is synonymous with y. It's just a different notation. And it's basically it's saying function f's value when I plug in a number for x. All right, so like if I wanted to say, let's say actually real quick example, side note, little recall. I guess I have to do recalls in a different color now, don't I? If I had f of x equals 2x plus 1, and I wanted to calculate what is f of 3, that means I'm plugging in 3 for x, right? So that'd be 2 times 3 plus 1, and I'd get f of 3 equals 7. right? Because 6 plus 1 is 7. So this is saying that the function, when I inputted 3, I got a 7 back as the output. F of 3 was 7. So better than just saying y equals 7, this actually kind of has the function's name, it's got the input and the output all in that same notation. So that would be like 3 comma 7 if I want to write it as an ordered pair. So you've seen stuff like that before, perhaps. So that's just function notation is what that's referred to as. So f of x is how you read that. So let's talk about, if I have my quadratic written in these forms, what way could I calculate some of my significant points? Right? If I wanted to find, say, what the vertex was, what my x-intercepts were, what the y-intercept was, what the axis of symmetry was, this is actually how we would find, let's say, the vertex. So the vertex is referred to as h comma k. All right, and graphically speaking, the vertex is the turning point of our parabola. It's possible also to have upside down parabolas, where instead of a valley, it's a mountain. And the vertex is the turning point, the place where it changes direction. And it turns out we've got this awesome handy-dandy formula to find h, which is referred to as the x-coordinate of the vertex.
Oh boy.
And that formula is negative b over 2a, which, actually, never mind, you guys don't know the other formula, so I'm not going to confuse you with mentioning another formula right now that this one gets mixed up with. Good stuff. So h equals negative b over 2a is how you find the x-coordinate of the vertex. How do I find the y-coordinate of the vertex? Well, once I know what h is, I can just straight up plug this into the function for all of its x's, and I would then just evaluate it. So once you know the x-coordinate, you just plug it in and find the y-coordinate, is the idea. So that's how you'd find h comma k, the vertex of a parabola. Sometimes, by the way, my own notation, I've referred to as h as v sub x and k as v sub y. That is not standard mathematical practice. We'll just refer to it as h and k mostly. So, good stuff. Other significant points you might want to know are the x-intercepts. And I'm not going to have you write down this whole thing, but the general idea is to find the x-intercept, you set the function, actually I'll write it in white over here, set the function equal to 0. And then solve. All right, is what we do. So you could just write down this, the top part, the top two lines here. X-intercept, you take f of x, set it equal to 0, or I guess if you wanted to write it this way, actually, yeah, these two lines are good. Right, or what do I mean by f of x? I'm referring to the whole function, and I'm setting it equal to 0 and solving. This is sample work as to how you might solve that. But we could, later on we'll find out we have other techniques of solving that as well, like for instance quadratic formula. And the x-intercepts I'll refer to as S1 and S2. And like I said earlier, S1 and S2 can also be referred to as not just as x-intercepts, but also as roots and zeros and solutions. Those are all relatively synonymous with one another. And now for everybody's favorite, the y-intercept. Why is it everyone's favorite? Because it's the coolest, most simple formula in the world. It's just c, whatever c is. What do I mean by c? I mean this c right here, whatever your value is going to be. We're going to get an example in here today too, so don't you fret, my friends.
Never fretting.
Yep. So the y-intercept is the whatever c is. So 0 comma c is how you could write that out as an ordered pair if you were worried, wanted to have it written that way. And let's see, the last thing I'll fit on this side of the page will be the axis of symmetry. And I did kind of mention that a little bit earlier there. Axis of symmetry for a parabola is the line at which the parabola is symmetric. Right, and the cool thing about the axis of symmetry is it will always pass through your vertex, h comma k. Right, and x equals h is its equation. Don't tell me ever that the axis of symmetry is just h, or your number. So don't just be like, oh, my axis of symmetry is 2. That would be wrong, because the axis of symmetry is not just a number. 2 is a number. X equals h represents the equation of a line.
That color for the dotted line is beautiful.
It is beautiful. I agree.
I
Wow.
like that orange you just had with those two colors.
No, that ruins it. Oh.
Okay. Wow. Beautiful colors. Yeah. YouTube viewers, feel free to add any comments about what colors you guys like from my videos as well.
Team purple
Be
or
much
team pink?
much appreciated. So, a couple more things regarding parabolas before we do our first example. We'll talk about which way it opens. Which way does the parabola open? So which way it opens, what direction it faces, what the orientation of the parabola is. So opens up I refer to as like the letter U-ish. Opens down is when it's like that. And I guess I might also refer to this as kind of like a valley. And this one is like a hill. Right, so opens is kind of what I'm referring to there, right? So it opens up if a is bigger than 0. So if the number in front of my square term is positive, it opens up, right? So if it's something like y equals 2x squared, opens up. It opens down if I have something like y equals negative 3 halves x squared plus x, all right? And the way I determine that is based off of the value of a. So whatever that number is, if it's positive, it opens up. If it's negative, it opens down.
Yeah, I have a little way to remember that.
Yeah, what's your way?
So you know that little valley one is going up?
Yep.
It looks kind of like a smiley face.
Oh, so
You
up,
have to
like it's
see
happy.
it. Yeah, you're like looking up to the future, you're really happy. And then the other one is a frowny face because you're looking down towards hell.
Oh, ooh, terrible. It's terrifying even. Okay, now the shape. This one's a little bit harder for me to describe. It turns out parabolas can be stretched or smooshed, or, yeah, vertically speaking. So imagine a regularly shaped parabola. We'll know what that means. Would be like this. A stretch would be if the parabola is narrower. All right, imagine I took a parabola and like stretched it like a piece of gum vertically, right? It's getting skinnier. Whereas what I mean by a vertical smoosh is like that same piece of gum. All right, here's where it would have been originally. If I'm smooshing it down, it's now going to be getting wider.
Why though?
Well, like think about when you smoosh silly putty.
It's stretching this way and it's smooshing this way.
So a vertical smoosh, right? I'm pushing down on it. A vertical stretch, I'm pulling up on it. You could also think about a vertical smoosh as a horizontal stretch. I just like using the word smoosh because,
I kind of like that word.
yeah, who would ever use that ever? But yeah, so that's what I'd like to think about that as. And my last fact about parabolas, this is like pretty awesome, sweet stuff. It's a cool property about parabolas that I think makes graphing them so much easier, where you actually only need to know the vertex and these quote-unquote slopes.
What is this?
Yep. Feel free to use some paper. It's fine. It's worth it for your learning. Those trees died for the sake of your brain cells, so it's gonna be It's going to be good. Don't let that tree die in vain either. That'd be terrible if it like gave its life and said, learn! And you're like, meh. Right? It'd be sad. It'd be so sad. That tree gave its life for you. Make this worth it, is what the tree's saying. So,
What?
all right. Let me talk about parabolas. It turns out that if I wanted to, so say here's my vertex. If I go up 1 and over 1 from my vertex, that's actually going to give me another point on the parabola. So it's pretty sweet. If I go up 3 from there and over 1, that will give me another point on the parabola. If I go up 5 from there and over 1, that will give me yet another point on my parabola. So it turns out I can kind of use that to get me some more points without having to do a lot of calculations. All right? And the main idea here is that the consecutive odd numbers are the rises of my slopes. Right? So next from that point would have been 7, and then 9, and then 11, and 13. So this is just like, actually, this property has more to do with just differences between consecutive perfect squares is really what it has to do with. That gives me this property. But it's kind of cool. It's kind of cool. And so a is the number in front of my x squared term. If a is equal to 1, this is what I refer to as a regularly shaped parabola, where it's just up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1. Anytime a is different, if I've had a smooch or a stretch, all right? And so say my a was 2. This is what this is saying. I would have instead, for an a of 2, gone up 2 over 1, up. Instead of 3, I would have gone up 6 over 1. Instead of 5, I would have gone up 10 over 1. So I would have just doubled all of these values, multiplying them by a, and that's what I'm trying to indicate there, there, and there. All right, so the slopes are going to be actually a really good trick for you to get the proper shape of the parabola.
That reminds me of Mousetrap, like board game.
Yeah, yeah. Tell me about it.
Go ahead, tell them about it.
I have a little diagram with like little turns and corners. Kind of reminds me of Mousetrap.
Okay. Sure. Let's do our first example.
Okay.
All right, so I said graph and find all significant information. So all significant information, I'm referring to the vertex, the X intercepts, the Y intercept, the axis of symmetry, the slopes, which way does this open, blah, 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 blah. All that stuff that we just talked about. So hopefully we'll get this one example done, and yeah, we'll get this done, I think, yeah. So first of all, let's find the vertex. Or, you know what, before we even do that, could you tell me what A, B, and C would be?
I can.
What's A?
A is x the second.
Ooh, that would be your quadratic term, but what is its coefficient? 1. All right, so it turns out, all right, and that's a common thing. That's why I take the time to do this.
So B is just 6, no x is b.
So B is actually -6.
What? Okay.
All right, thank you for trying. I'm glad you are, and that's why this is how we learn. I mean, you didn't see this before, so we're just doing this for the first time. So B would be -6, and then what's C going to be? 5, right?
I got 5.
So it includes the signs of those for A, B, and C, but it does not include the variables, right? So that's A, B, and C. So if I want to find the vertex, I do that using my little formula, H equals -b over 2a. So I'm going to plug in to find H. So H is equal to negative of -6 over 2 times 1, right? So that means that's +6 over 2, or H equals 3. Good stuff, good stuff. Yep, yep. Now, to find K, that's when I do F of H. So that means what I'm going to...
Vertex is 3. No,
Nope.
H is 3.
The x coordinate of the vertex is the 3. So to find k, I'm going to figure out what is f of 3 going to be. And that means I'm going to plug in 3 for all of these x's. So instead of x squared, it's 3 squared. Instead of minus 6x, it's minus 6 times 3. And then plus 5. Plus 5 staying the same. Constantly the same. So that's what? 9 minus 18 plus 5. So that's negative 9 plus 5. K is negative 4, I believe. So that means my vertex is the point 3 comma negative 4. All right, not too shabby. No, not bad at all. So I just straight up used the formula, and then I plugged it in to find the other coordinate. And that's my vertex. Let's find the x-intercepts. So how do I do that? That's when we set the function equal to 0 and solve. So what was my equation? X squared minus 6x plus 5. So I'm going to say x squared minus 6x plus 5 equals 0. And let's just solve this by factoring, friends. So that's 1 and 5. Which of those add to be 6? 1 and 5. I like it. Perfect. Also, if it's not factorable, later on we'll have a couple other techniques of solving this. But right now, it's working by factoring. You could have used like quadratic formula, but we'll practice all those later. Let's see. Their signs have to be the same because they multiply to be positive. So it's either plus plus or minus minus, but they add to be negative. So it must be minus minus. And now what I would do is set each of those equal to 0 and solve.
So what's x plus 1?
So x equals 1 or x equals 5 are my solutions or x-intercepts. So graphically speaking, this is the point 1 comma 0 and 5 comma 0. Sometimes students try to like mash those two together and they're like, oh, it's the point 1 comma 5, which funny enough will never be on your parabola if you try to put those together. So yeah, so don't do that. Classic. All right, y-intercept. That's just the 0 comma c. So what is the y-intercept of this equation? 5. Yeah, just straight up cinco. So I'll write that as 0 comma 5. Technically, you could say the y-intercept is 5, and that's accurate if you just give me the coordinate of that ordered pair. I like, since we're graphing this especially, I like kind of giving it to me as this. Let's see, what else do I need to know? What was the order of things? Let's see, then I have axis of symmetry, which I'll just abbreviate as AOS. Axis of symmetry, which is going to be x equals h, according to our formula. So that's x equals what number? 3. H was the x coordinate of our vertex. All right, how about which way does this open? Well, we happen to know that a is equal to 1, and we know that 1 is bigger than 0, so it opens up. Oh man, I'm running out of room fast. That's fine. What about the shape? Is it stretched or smooshed? Well, a is actually equal to 1. So it's actually a regular shape. What I'll call a regularly shaped parabola. And then lastly, slopes, which are going to be a times 1 over 1, a times 3 over 1, and a times 5 over 1. So my slopes are going to be 1 over 1, 3 over 1, and 5 over 1. Because my a happened to equal 1 in this case. So, let me get some nice graph paper here. So let's see, where's my vertex again? So I know where to make my grid. Let's see, vertex is 3, -4, opens up. So 3, -4 opens up. Over 3, down 4. There we go, there we go. Actually, you know what? I'm going to get a different snapshot. I didn't like that one. I think I don't need to go over as far. And then I'll have a better resolution. I can draw it a little larger. So, to graph this, our vertex is at over 3, down 4. Right there. Right? Our X intercepts were what points? 1 and 5. So one's right here, and one's right there. Our Y-intercept was +5 as well, right? Wasn't it? I believe, yeah. Now, using my slopes technique, I can actually find a whole bunch of points, which is nice. So the slopes from my vertex, if I go up 1, over 1, there's a point. Right, so I did that by going, let's see, what's a good color to use? Maybe I'll use this color. Right, up 1, over 1. Up 3 over 1 would be the next one. And notice that gave me one of my x-intercepts in this case. Not always the case. And then from there I would go up 5 over 1. So here I just gained another point. Right? So the coordinates of this point look like they'd be over 6, up 5, if I wanted to know where that was specifically. And then from here I could go up 7 over 1, which would land me at 12 or something like that. But and now, if I didn't know these points yet, let's say, I can actually, once I do my rises, using the property of the axis of symmetry, I can actually just mirror a whole bunch of my points over that axis. So for instance, this point is 1 unit to the right, so that means 1 unit to the left has to be another one. This point is 3 units or 2 units to the right, so that means 2 units to the left. There was another one. This one is 3 units this way, so that means 3 units to the left. There was another one. Okay, so if I didn't have those points, I could actually find some more. Or up here at 12, there would have been a point that would have been 4 units away, so 4 units this way would have been another one. So I can actually find a bunch of those real quick, which is nice. And then I'll draw the best smooth curve that I can, where it hopefully doesn't come to a sharp point. And something like that would be my parabola. So, so not bad. Now tonight, there will be some problems where they originally give you a quadratic that's equal to 0, and it'll say solve by graphing. All right, so instead of this, they maybe would have at first had it just equal 0. In order to do that, what you're going to do is just say, I'm just going to write this as a function, forget about 0, and replace 0 with like f of x or y, one of those equivalents. And then you're going to graph it using all of the techniques we just did. And then once you graph it, the solutions to the equation will actually be the same as the x-intercepts, is what's going on. All right, but that's the general idea for graphing. We're going to spend another day on this tomorrow. But thanks for watching, Internet friends. Bye-bye.